I'd like to walk you through the transformative journey that made the Netflix experimentation platform Scientist-Centric. This journey led our engineering teams to develop experimentation frameworks, grammars, and programmatic interfaces that leveraged and were inclusive to data scientists and their domain expertise, which was critical for producing the best platform for online experimentation. At Netflix, we utilize experimentation in multiple parts of the business, including product, operations, growth, and even artwork. Imagine you open your TV. How should Netflix use visualizations to show all of its content? When it comes to Stranger Things, do we use artwork to highlight the kids in the show, or the fact that it's a thriller, or perhaps different artwork will attract different users, like this throwback feeling to people that grew up in the US in the 1980s. We optimize the artwork through data and experimentation, and we also relay that information to our partners creating the images. Now, in order to support hundreds of other experiments at Netflix, we need a powerful experimentation platform. And the typical architecture for such a system starts with data logging. Who is in the experiment? What are the KPIs? And what are the other important dimensions? For example, how long has the customer been a subscriber with Netflix? And from those logs, we go into a series of Spark jobs that join several tables together in ETL. And we calculate statistics for users, like the total number of hours streamed, and the total number of retained users, so on and so forth. These statistics are loaded into Elasticsearch or Druid for fast indexing and querying, which ultimately serves the platform's interactive dashboard. But the trouble with this old architecture is that there is an explosion of technologies that are difficult to manage. And furthermore, it's difficult for scientists to manage and difficult for scientists to contribute. As engineers, we have these habits and we also have these responsibilities to keep up with cutting edge software, but it's not the scientist's responsibility. And Netflix was not fully leveraging its top data scientists to do cutting edge analytics. To change that, we recognized that the design patterns for the experimentation platform needed to become science-centric. In order for the platform to do this, we needed to design around three key tenets: trustworthiness, scalability, and inclusivity. We want to be inclusive to that group of data scientists. The first two you all know, but to accomplish this while being inclusive is hard. But being inclusive is also necessary in order to let scientists from diverse backgrounds contribute their unique domain knowledge to the platform. Being inclusive meant we needed to be open to languages like Python and R that data scientists use, and ready to absorb packages like pandas, stats models, and dplyr. Moving towards a science-centric experimentation platform, we engineered a few narrowly scoped libraries that allowed data scientists to contribute to data, modeling, and visualization while still preserving key engineering principles like trustworthiness and scalability. The two libraries I'll talk about in detail are called Metrics Repo and Causal Models. Metrics Repo is our Python framework for orchestrating data, analysis, and rendering of our reports. It allows data scientists to make targeted contributions for the platform while preserving its trustworthiness and scalability. Metrics Repo enables a pattern for data that allows users to compose and contribute programmatically generated SQL that runs on Spark. And this programmatic nature supports Metrics Repo's open and inclusive policy for contributing data sources. In this example here, a user is building a query class that interfaces with tables in order to auto-generate SQL, removing hard coding and allowing safe inheritance. Metrics Repo also ships a powerful testing framework that includes unit tests and integration tests analyzing data end-to-end, guaranteeing consistency in data sources and metrics. This framework creates an attractive environment to centralize data and metrics definitions in a standard way, supporting the scalability of the data store. After configuring data, users can also configure the analysis options for their metrics. For example, they can specify that their metrics are proportion metrics or rare event metrics, which will configure the analysis appropriately. Then they can also configure the visualizations for their metrics. In Metrics Repo, in order to support an open policy, Metrics Repo takes care of an enormous amount of surrounding engineering infrastructure. For scalability, it parallelizes computation across several Docker containers and through several processes that run in each container. It also handles robust software deployments through hooks into Spinnaker. And finally, it also acts as a bridge for the UI interface of the experimentation platform, so that anytime new data or metrics or metric configurations are updated, they can be automatically rendered in our dashboards. The second library that I'll talk about is Causal Models, which is our Python library for statistical modeling of causal effects. In this example, I'm showing we are utilizing different models in order to produce a rich analysis of causal effects, ranging from the average effect in an experiment to the average effect for a segment of users, to the trends in the effect for a segment of users. And like Metrics Repo, Causal Models centralizes and standardizes implementations for models that are relevant for the experimentation platform. The library continues the theme of having an open contribution policy and has seamless integration with Metrics Repo, so that all statistical models are automatically included in the deployment process. After contributing a model, a user can use Metrics Repo to configure their metrics to be analyzed with their new model. Causal Models is a highly optimized library in order to give data scientists scalable computation of causal effects. And we are able to compute hundreds of causal effects on large data sets in seconds. First, numerical computing all happens in C++, where we control memory efficiently. Second, we utilize a data compression strategy for conditionally sufficient statistics that reduces the data volume so much that you can analyze data on a single machine. And finally, the library is optimized for sparse linear algebra. And altogether, all of these are software improvements to help data scientists scale their code and empower them to make direct contributions with the experimentation platform's open policy. The separation of these libraries allows easy contribution, but the libraries also retain strong interfaces to bridge them. Users of the XP can toggle the way they analyze an experiment to suit their data and their assumptions. They can pick any combination of metrics, models, and visualization, which creates a very attractive environment for anyone to explore and learn. And to conclude, I want to share the impact of this shift to being more science-centric. The integration of libraries and tools that data scientists use has increased the learnings our platform can offer. The platform is able to leverage better models for analysis, and these new models improve sensitivity in our metrics, sometimes by 60%, and show deep insights into segments and trends. At the same time, the integration has improved our human efficiency. Team leaders can rely on the fact that the platform can be developed by both engineers and data scientists. There is a large interdisciplinary focus going on across both communities. It has created a technical symbiosis where data scientists are gaining skills and spending less time productionizing their work, and in turn distributing their domain expertise to improve the company. Thank you all for having me, and please reach out if you'd like to discuss more.